I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for the student, and I pray you help us use this time wisely, Lord. In your name I pray. Amen. I'm not sure if I'm going to do this if no one shows up. I might, I don't know. Let's see here. So, I think what might be useful is to take a swing at some of these in chapter 6, maybe. Try one out here. Let's see here. Oh, no, that was not chapter 6. I meant it was chapter 7. Let's look at number 13. Yeah, look at number 13. This one may be too easy, I don't know. G is a group. The order of the group is 60. All right. So the question is, what are the possible orders for subgroups of G? I guess this is too easy. So let's see here. What are positive divisors of 60? 1, 2, 3, 4. Yeah. 5, 6, 7, 8. Is 8? Oh, I don't think 8 divides. 9. Not 9. 10 though, yeah. 15. Yeah. Oh, what about 12? 12. Let's see here. We said 15, yeah. And of course 20, and then 30, and then of course 60. So the possible orders of subgroups, there you have it. Here, I'll check the answer just to make myself feel better. I don't really need to check the answer on this one. I'm just being silly. I'm mostly checking to see if make sure I didn't check if it's a number. 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, 60. Yay. All right. I think our whole test that problem right there. Yeah. Let's do number 14. Have I assigned 14? I don't think so. Oh well, if I have, I have. Number 7 you got on that page so far. Okay, so here we have K, a proper subgroup of H. Okay, a proper subgroup of H, and H is a proper subgroup of G. All right. And we're given that the order of K is 42, and the order of G is 420, right? The question is, what are the possible orders of H? Say 42 would be, yeah, let's see. I guess what I'd say is, so if G, so first of all, one of the things we have is that the order of H, right, is less than 420, which isn't especially enlightening. But we also know that the order of K is less than the order of H, right? Oh, I'm sorry, the order of, yeah, Yeah, H. Oh, okay, so 42 is less than the order of H, is less than 420. But this also has to be multiple, right? Of 42, and divisor of 420, working Lagrange's theorem both ways. I don't know if that says. So what does that mean? So your choices are, so those I can start enumerating, right? Like, what are multiples of 42? 84, but it's not 42, right? It's a proper subgroup. It's not 42 itself. So you either got like 84 or 3 times 42, which is 126, or 4 times 42 is 3 times 42. Yeah, that's that. 4 times 42, 160 plus 168, right? 5 times 42 is 210. Right? And so forth. I think that's all I can go to. Well, it's a proper subgroup, and so I think that's as far as I can go because that's half of this. So are any of those blue numbers divisors of 420? $84 is? Yes. So we have either 84, could have the order, so the order of H could be equal to 84, or, I don't think 126 is a divisor though, is it? But 210 is. So there you go. Have fun. Now I will tell you this. There's one of the problems in the homework. I think it's due tomorrow. It's important to use the back in I think chapter. Oh man, where was that thing? Maybe it's in chapter. I don't remember. Just a second, I'll find it. Yeah, this is the one I have not gone up. No, that's not it either. Where's that stupid thing? There's this theorem about H and K and the intersection of H and K. Golly, where is that theorem? I have not covered it in class, but it is relevant. I don't know where that thing is in here. I'm slightly worried because I found it in a different. I have a new edition of this book, and I found it in there. I'm pretty sure it's in the old editions too, though. Oh, no, that's not it. Come on. It's driving me nuts. I don't know the name. Oh man. Well, oh well. You can ask Lorenzo. I showed her it earlier. Well, I know the theorem though. I think. Oh man, do I know the theorem is a question. I want to say. Dang it. It's a theorem that concerns the product of two subgroups and the order of the product of two subgroups. And goodness gracious, just not something I have in my mind yet. I haven't taught it to you guys yet, and I don't have it memorized, and it's not that complicated, but I don't want to misstate it either, you know.
Would be in chapter 8 somewhere.
Maybe. I mean, the definition is on page 182. Well, that's if G is equal to. This is most annoying. I didn't. I should just give up on it. Sorry. That's stupid theorem. Let's see here. Okay, so if we had H is a normal subgroup of G, and K is a normal subgroup of G, right? And H intersect K is the identity, right? Then what did that mean? Yeah, I think G was equal to HK, right? Which is kind of a funny definition, because this thing has another definition, just like, this is sometimes just defined to be like product x, y such that x is in H and y is in K. I'm not sure if I'm missing something here. Anyway, so I think basically it's that the order of G is equal to the order of H times the order of K is true here. But that's not quite the thing you need for that other problem in the homework. So I'm not being helpful. Let me just shut up about this. It's because the H and the K in the homework don't have to necessarily have an intersection of the identity. Yeah, so if like H and K have order 12 and 18 respectively, if they intersected at the identity, that would mean that product, you can form the product subgroup H times K. Like, oh, didn't I say not HK, but I said, wasn't it H times K?
It's HK.
Was it HK? Oh man. All right. Well, I'm going to have to do some. I'm at a notational impasse at the moment, but it's not interesting. So let me stop. The point was, if I had the intersection of H and K was the identity, then I think that would mean that the product H and K had order 12 times 18, which is impossible because the group only has order 36. So you're anyway, I gotta find where I found that. I guess I found the theorem maybe there's a theorem in the later edition, which is not in this edition, which is weirding me out because I thought they were the same. But oh well, I guess I'm happy if it's, you know, we spent several $1,000s less collectively doing this, so it's probably a win.
$10 versus $200 a piece.
Mm-hmm.
I was thinking.
Okay, so suppose we look at, let's say D3 equal to 1x, x squared, y, xy, x squared y. I wanted to look at the left multiplications for a second and kind of like think, I want to show you kind of a weird idea. So if I have like left multiplication by x, how's that go? Yeah, one goes to x, very good.
X goes to x squared.
Right.
X squared goes to 1.
Let's see here. Yeah, I should do it like that. 1 goes to x, and then that goes to x squared, right? And then this goes to back to 1. Y goes to what? xy, right? And then that goes to what? X squared y, very good. And then back to y again. All right. Is that everything? 1x. So in other words, you could write Lx as a sort of cycle, right? You could write it as a cycle. 1 goes to x squared. And then y goes to xy goes to x squared y. If you're willing to generalize the cycle notation to abstract elements rather than just the numbers 1 through n. But we don't want to do that. I mean, we could do that, but the homework problem I've assigned you guys doesn't do that, right? So instead of doing this, what we do is we enumerate. I guess the homework is on which, it's not on this, it's on the quaternion 8 group, right? Yeah. So this is like 1, but if I was to endorse that here, 4, 5, 6, oh, I can't count. Oh, okay. Then this, L sub x, would be, I mean, this is, it's not, I mean, you could say this is straight up equals, but this would be corresponding to, you know, 1, 2, 3, 4, 5, 6, right? And so there's a representation. You can view D3 as a particular subgroup of S6. Like, what is that subgroup? Well, the subgroup of S6 that it naturally corresponds, well, one of the cycles in there is this, right? Yeah, let's find it. So there's the L sub x. What happens with the next thing in the story here? X squared. 1 Lx squared goes to what? It goes to x squared, which then goes to x, which goes to 1, okay. And then, so you go y goes to yx squared goes to, oh, I'm sorry, I'll get it with it eventually, your x squared y, it's been a long day. And then xy? Oh, back to y again. So basically, Lxy corresponds to, oh, Lx squared, yeah, I'm an idiot. Lx squared corresponds to, this would be in the number, I mean, in the abstract cycle notation, 1 x squared x, right? And then y, x squared y, xy, right? Or if we're, instead of using the abstract cycle notation, if we're just saying we're looking for specifically the subset, subgroup of S3, which is isomorphic to D3, then this one we would use, what's that? 132, right? What's that?
465.
465, yeah. And let's see here, what else do we have to figure out? Now, if I was smarter, I wouldn't have done that, right? Because Lx squared inverse, right, is Lx. And this is a faithful correspondence, so like inverses go to inverses. And so that is straight up, these are inverse. So I could have figured this out without doing calculation like I just did. Let's continue. So what's the other mappings we have? Yeah, Ly. So we go 1, goes to y, goes to 1, right? And then how about the x, and then x goes to xy. Oh, wait a minute. Well, yx, right? Which is equal to x cubed y, right? Oh, wait a minute, x squared y here? Because, yeah, x inverse is x squared here. And then that goes to y, x squared y, which is x, I think. Because that's x to the minus 2 yy. But x to the minus 2 is x again. We're back where we started. X squared goes to yx squared, which is equal to xy. And that will go back to x squared again, I'd bet. Right? And what else is there? Did I get everything? xy goes to yxy, also known as x squared, and that goes to yx squared, which is also known as xy, right? Is there anything else? X squared y. So x squared y goes to yx squared y, which is equal to xyy, and then x goes to yx, which is x squared y. Okay, yeah. So basically, Ly is, in the abstract notation, it sends x to x squared y, and then back again, and then it sends x squared to xy, and then back again. It sends x. Wait a minute. What?
It should end up being 142536.
What did I do? Did I do something wrong in here? Why do I have? Oh, this is the same. I just did the same calculation twice. That's dumb. I shouldn't have done this. One of these I shouldn't have done. Right? I'm about to write the same. Idiot. Okay. These are the same cycle. And then that's x squared y. There's 6 things, right?
Yes.
Okay. So, I'm sorry. I'm trying to stop being a doofus here. X squared y goes to x. But I already got that one. What's wrong with me? I already did that one. I'm an idiot. Look, I mean, x squared y is up here, right? I don't need to do it down here. Like, asked and answered, you know? Like, done. Don't need to do those. They're already done. So, what? I mean, is there anything else to do? What am I missing?
1 goes to y.
Ah, that's the one. Okay, so and then you were saying that this in my I would say that you could say that these are equal, you know, in a sense that, I mean, you could, if you wanted to introduce this notation for permutations on D3 itself, that would be like a reasonable notation. That's what I would mean by that anyway. These are actually a funny notation for permutations on D3 itself. Whereas that corresponds to the particular subgroup, particular element inside S6. What did you tell me what this one was what?
I had a different order. I had 1, 4.
Okay.
So, yeah.
So that was 1, 4, right? But this is 3. Oh, I'm an idiot.
You get to 1, 4, 2, 5, 3, 6.
Let's see.
Oh, wait. No.
Right now we have 2, 6,
Yeah.
and then 3, 5, and then 1, 4.
You just had them in a different order, and that's cool. So that one. And what else is there to calculate? We have,
LX1, LX squared y.
let's see here. Well, I'm starting to get tired of this, but so xy, lxy.
Just some sort of there to shorten that up or accept it in brute force.
Not that I know of at the moment. I think after you do this for a while, you get more insight and it gets faster, right? And you stop making dumb mistakes like I make. But yeah, certainly 1 goes to xy, which goes back again, right? Y goes to xyy, also known as x, which then goes to xyx, which is really y again, right? And I got xy, I got 1, I got y, I got x. I should check x squared. X squared goes to xyx squared, which is really x squared y, yeah? And then that must go back here again. So this one is really 1 xy y x squared y, aka 1, 5, 4, 2, thank you, and 3, 6, yeah. And then what else do we have to figure out? X squared y. All right, so Lx squared y. 1 goes to x squared y, goes back again. X goes to x squared yx, which is also known as what? X, yeah. Really? Oh, that's xy, right? And then it goes back again. And then x squared goes to x squared yx squared, which is also known as y, right? And then it must go back again. I know it has to go back again because the order of L, that's not quite right. I mean, anyway, so let me not say things I'm not sure about. So this gives me the cycle I get. From this, I get 1, 6, 1, 6, 2, 2, 5, 3, 4. Yeah, these are the times that you're happy that I let you guys work together. Let's see here. And I think that's it. We got all 5 of them, right? So apparently, D3 is isomorphic to the set. Let's see here. Obviously 1, right? And then you got your 1, 2, 3, 4, 5, 6. You got your 3, 2, 1, 6, 5, 4. right? And then you got your these transposition-y things here, like you got your 2, 6, 3, 5, 1, 4, and your 1, 5, 4, 2. Oh man, these are awful to grade. 3, 6. And what else is there? 1, 6, 2, 5, 3, 4. Anything else? Did I miss any? 1, 2, 3, 4, 5. Oh, that's 6. So there you go. That is a subgroup, obviously not equal to, right? It's a proper subgroup of the symmetric group. And that subgroup of the symmetric, that subgroup of the, yeah, I don't know where that 3 came from.
That's D3.
It's D3. Yeah, that's probably it. But there you go. In fact, so there's another version of Cayley's theorem. Now, the way I stated Cayley's theorem, it didn't quite look like this, right? But the other version of Cayley's theorem basically says that every finite group is isomorphic to a subgroup. Every finite group of order n is isomorphic to a particular subgroup of the symmetric group of order n. Symmetric group in n letters, which of course has order n factorial, to be more clear. So anyway, I thought this might possibly be helpful for that one homework problem. So do you have any questions?
Like to work on?
Yeah.
Or about this?
All right, well, in that case, let me talk about the quaternions a little bit. So we've got this quaternion 8 group that we've been playing with a little bit, right? Q8, which was plus or minus 1, plus or minus I, plus or minus j, plus or minus k, right? And this is different than the quaternions. The quaternions is this set. It's A plus BI plus CJ plus DK such that A, B, C, D are in the reals. This is the quaternions. So those are like all possible linear combinations over the reals of the quaternion 8 group. But otherwise, you multiply them and add them just like normal. It's just that I squared is minus 1, j squared is minus 1, k squared is minus 1. And some really cool stuff happens. See if I have time to show you. Maybe, maybe not. So if you take A plus BI and yeah, let me just multiply it out. CJ plus DK, right? And if I multiply that by another one, let's say T plus XI plus YJ plus ZK, what happens? So basically, this is the definition of multiplication I'm showing you, but the definition is made so that distribution works like you'd expect. So I get like AT, I'll write the real part first, minus I times I is minus 1, so minus BX, minus CY, minus DZ, all right? And then plus, there are going to be 16 terms here, plus I. All right, how do I get I? So here's the thing. I, J, and K, it's like a circle. This is just like Calc 3, right? In fact, Calculus 3, the IJK notation there, comes from this. This is Hamilton's quaternions. This was what we used for vector analysis before we had vectors. And so when vector analysis came along, they borrowed the IJK notation from Hamilton's quaternions. and it persists to this day as a very poor notation for vectors. We ought to be writing vectors like this, guys. This is a way, way better notation for vectors than IJK.
I've seen that notation.
Yeah, this is a much better notation because so many reasons. But anyway, historical reasons we use IJK. I don't when I teach Calc 3, but whatever. So the way I can get I, how can I get I? I can get I from j times k equals to I, right? I can also get I from what? From 1 times I, right, is I, or I times 1 is I, right? But also k times j is minus I. So those are the 4 different ways I can get I. So starting with AX, then BT, right? And then JK gives me I, so plus C times Z, and then minus D times Y. Plus J. So J here I have, of course I've got like C times T and A times Y. And then let's see here, J, trying to get J's, right? So I times K, what is I times K? I times K is, minus J, right? So minus B, what did I just say? Minus BZ plus, lost track. Where am I? D what? DY?
Yes.
No. I'm trying to get a J.
dx.
Oh, my dx. Yeah, dx, okay. All right, plus k. And so I'll do the easy part. A z plus dt, right? Sorry, I'm not entirely consistent in my selection of terms. Sorry about that. And then I times j, which gives me a b, by, and then j minus c, cx. All right, and there you go. That's the full quaternion product. It's a way of multiplying 4 vectors. This is a product of R4, and the cool thing about this product is, there's an inverse. So you can define a conjugate, A plus IB plus JC plus KD. Conjugate is defined to be A minus IB minus JC. I'm messing up I should be saying BI minus BI minus, I was trying to write the constants on the other side. Sorry. Just to be consistent. Anyway, so that's the quaternionic conjugate. And you can show that 1 over z, right, is equal to z bar over zz bar. And so I think that still makes sense. There's still a way of finding a multiplicative inverse that will actually define a multiplicative inverse for a quaternion, provided it's non-zero. So every non-zero quaternion has a multiplicative inverse. But the rub is, and so there's a way of multiplying quaternions. There's a way of, adding quaternions is easier, right? So it's got an additive structure, it's got a multiplicative structure. There's a number 1 in there, that's the identity. everything has a multiplicative inverse as long as it's non-zero, right? So like in the non-zero quaternions, we have inverses. So it's pretty much everything you need for a field, right? Every non-zero element of this space, which is a ring, has a multiplicative inverse. The thing is, it's not a field because I times j is not equal to j times I. See, ij is not equal to ji because this is k, but this is minus k, right? So the quaternions are what are an example of what's called a skew field. So it's like it's almost a field, but it's not quite. In fact, if you asked me for another example of a skew field, I couldn't give it to you. This is the one I know. But if you tilt your head and squint and look at this, and you instead of looking, you could look at this as like a plus a vector times, let's say, t plus r vector, right? And then you start looking over here at what this is. Can you see what this is? So here, of course, I'm saying the a vector is b, c, d. The r vector is x, y, z, right? Maybe I should use a w down here as to not confuse. So yeah, I'll use a zeta, just to be weird. So look, this is like, see that? bx, cy, dz. The a and t, those are just multiple. So you got like at, right? That's just these two guys. And then minus a dot r. Right? See that? And then this stuff here, you've got a, let's see here, this guy, and this guy just gives me plus a times the r vector, right? And then, right, that's this one, d this exactly, plus t times the a vector, right? And then, so of course that's added, right? And then since I'm working on one board, I have to finish it here. Plus what? You got these terms. What's the first term in the cross product of A and R? It's CZ minus dy. But that's exactly what I have here. CZ minus dy. That's the ith component of the cross product of the vector A and vector B. So what you have, in fact, using this natural correspondence is A cross R. So the quaternionic product of two 4 vectors has within it the ordinary dot product of 3-dimensional vectors and the ordinary cross product of 3-dimensional vectors plus some extra pieces. So if you focus your attention on quaternions, which are just spatial quaternions, ones with like the A or the T component being 0, then all these things go away, and you're just left with dot product, cross product minus dot product. So anything you do in Calculus 3, you can do with quaternions just by the appropriate massage of these equations. Basically, it's all there to use. And that's why that's why people used quaternions for 40 years before we used vectors. It was a fight to start using vectors. Like, it was not because people, you know how physicists are and engineers, they gain some sort of metaphysical attachment to notation, right? That's right. Anyway, there's a rich, lots of examples in here. You have additive subgroups. There's 3 additive subgroups, which are the complex numbers, at least 3. There's many more. But it's pretty easy to see that if you look at the subgroup that's formed, like A plus IB, right? This is a subgroup of H with respect to addition. But it's also the case that, if you have A plus IB, such that AB are not equal to 0, right? That's a subgroup of the non-zero quaternions with respect to multiplication. So there's like additive subgroups, there's multiplicative subgroups. I drew this picture earlier. In some sense, it's like this. You've got like I, you've got J, you've got K like that, and in here you've got the reals. So there's like, this is one kind of complex number. I mean, there's like 3 copies of the complex numbers. They're orthogonal, and they all share the same real numbers. But anyway, there's all kinds of structure here. It's a really interesting example. Much more to say about it. But anyway, that's just wanted to share it with you guys. I'm not sure we'll get to it in class. I mean, I'll have homework on it eventually. So you'll reap the rewards of this discussion then. Yeah. I mean, that thing we just derived over there could make certain homework problems much easier. I don't know. I mean, you can view these as particular 4x4 matrices too. Sorry, but if you guys don't come with questions, I will ramble on. But I started late, so I started late. So anyway, I hope something we did today was useful.